There are a couple of things about Gauss's law that didn't make it into the lectures that I did put into class last week. So, first, how does it make sense that if we look at Gauss's law, the only thing that determines the flux is the charge enclosed in a surface rather than the charge outside? For example, let's say we have a charged sphere and we're looking at the electric field inside. And the red area with the dotted boundary here is our Gaussian surface. Right outside of it, we've got charges all through here, but right outside of it, we can see we've got positive charges right on top of it. We should have a very strong electric field there because we're very close to these positive charges. How does that not change the flux? The reason is what we're looking at in Gauss's law is the net flux through the surface. So it's the difference between what goes in and what comes out. If you look at the flux from one of these charges outside, there are lines going all the way through the red area. And I haven't shown many field lines here, but what you would notice in real life is these things spread out as 1 over r squared. But the area that they cover increases as r squared. So if you want a similar example, let's imagine this cube here is a tint. So the sides are kind of translucent. If we look at a flashlight, which also has a intensity drop off of 1 over r squared, if we have a flashlight outside the tint, we get a very bright small spot on the near side, and then on the far side we would expect to get a much larger spot, but it's also much dimmer. The reason is the intensity of light drops off as 1 over r squared as well. So while the intensity has dropped by a significant amount, the area has gotten bigger by the same amount. Area gets bigger as r squared, intensity drops off as 1 over r squared. The same thing happens for the E field. So what that means is the light coming in here would be equal to the light leaving here, or for the E field, the flux entering is the same as the flux leaving. That's why it doesn't matter if there are charges right outside the surface, because their flux goes in and right back out. Now, another point is the electric field inside a conductor is 0 in electrostatics. And electrostatics is what we've been doing so far. It's what we have when there are no batteries or generators. Why is the E field 0 inside that? The reason is a conductor, we define it as essentially something that has a large amount of free charges. This has nothing to do with net charge. So if we take a copper penny, and it'll have to be about 30 or 40 years old at this point to be copper, it's electrically neutral because we have the same number of positive and negative charges. But about 3% of the electrons in the copper are not connected to particular atoms, but they can go anywhere in the penny, anywhere in the solid. If we tried to put an electric field inside a conductor, the free charges would respond to it immediately. The positive ones would move downstream and the negative ones would move upstream. What the fields associated with those charges that responded are oppositely directed to the field that we put in place in the first place to make them move. So what happens is the total field returns to 0 very quickly, typically on a nanosecond timescale. So this is why we don't have persistent currents in electrostatics. If we drop charges on a conductor, they rearrange themselves in such a way as to kill any existing electric field, and then they stop moving, again, very, very fast. This is kind of like what you'd get if you decided you wanted to put a hole in the surface of a pail of water by scooping out some water. The water fills the hole right back in, only instead of a time scale of milliseconds, the electrons will remove the electric field on a time scale of nanoseconds. So if we can't have a persistent electric field in a conductor, what does that tell us about the location of any excess charge we put on it? We can use Gauss's law on our sphere again. Ordinarily, we use this so that we can find the E field given the charge distribution, but we can do this in the other direction. We already know inside a conductor, E should be equal to 0, but if E equals 0, then the left side has to be 0, and therefore the right side, specifically the enclosed charge, has to be 0. So what this means is we add a bunch of charges to our conducting sphere. They all have to go to the surface. Now, it would be easy enough to accept this if we were talking about a couple of extra electrons, because then we could say, well, all right, one will go to the North Pole, one will go to the South Pole. They'll be as far away from each other as they can be. If we have 3, we could put a triangle of them somewhere like the equator. For 4, maybe we'd have a tetrahedron shape on the sphere. The electrons want to get as far away from each other as possible, and what want really means is they want to get to a minimum of energy. The potential energy for a system of charges should look the same as the potential energy for a system of masses that we saw when we looked at Newton's law of gravity. Here we have the equations for gravity, the force and the potential energy. We had to put a negative in by hand here. For electrostatics, here's our force, looks kind of similar, and here's our potential energy. This does not require us to put a negative in by hand because there are 2 signs for charges, and opposites attract, likes repel. We don't have that situation with masses, they all attract. If we want to minimize the energy here, it seems hard to believe that the way to do that would be to put 1,000, if you have 1,000 or 1,000,000 or 1,000,000,000 electrons, they should all go to the surface and none go to the center to get away from everyone. That never really made sense to me when I took the class, but let's see if we can explain it now. If we have to have E equal to 0 inside the conductor and enclosed charge is 0 in that volume, let's imagine we keep expanding our Gaussian surface outward towards the physical surface, this thin blue area. As we move the surface outward, we can't have any charge inside it because that would mean we have an E field inside it, and we know we can't do that. The limit here happens when the Gaussian surface reaches the physical surface. When it's that big, then we can have charge outside of it because there's no rule about having an electric field in the empty space outside a conductor. What else would help us understand this? Well, the energy of a charge distribution would just involve calculating this k qi qj over rij. Notice that's not squared because we're talking about energy, not force. We'd have to calculate this for every possible combination of charges. That number of calculations will be n squared minus n over 2. So if we had just 3 charges, that's 3 calculations. If we had 10 charges, now we're at 45 calculations, and it just gets bigger and bigger faster. We wouldn't want to do this by hand. There's a spreadsheet in this week's lab that does this for 100 charges. Now, there's a website that I found, and it's cited in the comments of the program, that gave the coordinates for putting 99 points equally spaced on a sphere and for putting 100 points equally spaced on a sphere. What the program does is it does this sum. So for 100 points, you're looking at about 5,000 calculations. That's why we don't want to do it by hand. It calculates the energy of 100 points on the surface. Then it calculates the energy of 99 points on the surface and 1 in the center. And what you see when you do the lab is the energy is indeed lower when everything is on the surface. This is nothing like a mathematical proof, but hopefully it's a simple enough procedure to help you believe